All right, this next unit of study is combinations, and it's permutations with a twist. So what's going to make this different is that we're going to be looking at something where order doesn't matter in the same way. So let's look at some examples. How many ways are there to select co-chairs to represent 5 people? So let's think of these people as people A, B, C, D, and E. So those are my 5 people, and they are co-chairs. So with 2 people, how many combinations? So you might think through this, and I encourage you to try this out on your own, and I'll start this one out for you. So you could have A and B be the people that get selected. You could have A and C be the people selected. You could have A and D. You could have A and E. But notice that if I were to come up with B and A, that's no different than having AB, which is what makes this unit different. So again, if you have person A and person B versus person B and person A and they're co-chairs, really didn't matter what order you picked them in. So those are not unique. So we can keep coming up here. So B and C would be a different group. B and D, B and E, C and D, C and E, and lastly, D and E. So these are all the co-chairs. And so you'd end up with 10 different ways. Okay, so I want you to try the same thing here with 3 people. So here you would have A, B, and C would be one of the options. Okay, and let's see what answers you come up with in your trial. All right, let's look at the answers here. So if you had 2 people selected from person A, B, C, D, and E, there would be 10 different ways that we found there. If you had 3 people, there would also be 10. If you had 4 people, there would be 5. If you had 5 people, there would be 1 way, and that would be having everybody included. What you might not notice, if you really want to see the pattern, you're not seeing some kind of pattern, which is not easy to see. The next question would be with 1 person, how many different combinations? Okay, so that would be having just A or just B or just C or just D or just E all by themselves. That would give you 5. So you might notice that our pattern here went from 5 to 10 to 10 to 5 to 1, and that might bring up something you've seen before. I'll give you a little bit of a hint here. I want you to think about someone named Pascal. All right, permutations and combinations. Let's get a definition in here. So a permutation is the number of ways of selecting from a group of items where order matters. Example, how many ways can a president and vice president be chosen from 10 members? Or how many ways can a gold, silver, and bronze medal be given to 10 racers? A combination is the number of ways of selecting from a group of items where order does not matter. Key word here is it does not matter. Not. Example, how many ways can co-chairs be chosen? So in other words, there's no difference between the 2 roles as you saw up in the previous question with a president and vice president. Or how many ways can 3, and I didn't finish that question, how many ways can 3, let's say 3 ribbons be given to 10 racers? And what you'll notice there is it's not like a gold and silver ribbon. It's just a ribbon, just a ribbon. Okay. Combination notation. Let's learn some combination notation. Number of combinations is equal to the number of permutations divided by r factorial, where r is the number that you selected. For the previous example, the number of combinations of 3 selected from 5 is, and it's, I'll write it out again here. It's NPR over R factorial. So n is the number of people right here. So we're selecting from 5, and we're choosing 3 of them. That's the R item. So it's 5p3 over R, which is 3 factorial. And that gives us 5p3, which is, slipping my head right now, that is 60, and 3 factorial is 6, so 60 divided by 6 is 10. Okay. Combinations, a general form. Let's dig a little deeper into this formula. So write the following equation in factorial form. So if we have NPR over R factorial, if you remember the definition of NPR, so NPR is n factorial over n minus R factorial. And so what we follow that up with is we divide that still by R factorial, like that. Okay, well, if you're dividing by R factorial, we can think of that as multiplying by its reciprocal. So the reciprocal of R factorial is to switch this and do 1 over R factorial. So we have n factorial over n minus R factorial times 1 over R factorial. And we can simplify that to n factorial over n minus R factorial, and then we'd multiply it by the other R factorial. So a little thing to note here, something that you should know, NPR is equal to n factorial over n minus R factorial, and NCR is equal to n factorial over n minus R factorial R factorial. Okay, and the C there is for combinations, and this is for when order does not matter. And permutation, P is for permutation, which is for when order does matter. Now what's confusing is in textbooks, typically this isn't what it says. It says NCR. The N and the R are subtext. But some of the older textbooks that weren't able to use that subtext, they'll use this notation, which is C bracket N comma R. Or it will simply do this symbol here, which is N over R, or N choose R, we would say, with brackets. You'll notice that this is not a fraction, so it doesn't have a line in between there. It just has a number on top of another number. Let's look at some examples of that. Okay, combinations. Let's make this about pizza. When math doesn't make sense, we use pizza, and works for fractions. It should work for this too. So this is a dumbed down version of combinations. You're hungry and you want a pizza. There are 10 toppings available, but you can only afford 3. What are the number of combinations? So you can think of this as you have 10 and you're looking to choose 3 of them. And notice it wouldn't be different if you asked for pineapple and ham, or ham and pineapple. The order doesn't matter when you call in for this order. So order doesn't matter. So we would have 10 choose 3, which is equal to 10 factorial, because this is our n and this is our r. So it's 10 factorial over 10 minus 3 factorial 3 factorial. This is our n minus r, and this is our r. So to simplify this, we do 10 factorial over, and 10 minus 3 is 7. So we have 7 factorial, 3 factorial. So we can think of this as, and we can do this without a calculator here. So if you have a 10 factorial over a 7 factorial, that's like 10 times 9 times 8 times 7 factorial on top, and 7 factorial on the bottom with a 3 factorial. And what happens is these 7's factorials will cross out. which leaves us with 10 times 9 times 8, and 3 factorial is 6. Well, 10 times 9 times 8 is 720. Divide that by 6, and we're left with 120 different pizzas, which makes for a really exciting life after high school, because when you're looking to make yourself your own meal, you can go out and use 10 items at a pizza store, and you can get yourself 120 unique meals that year. What a fun opportunity to spend your money on pizza. All right, let's do some quick rapid fire round here. You have a deck of 52 cards. How many hands are possible with a 2-card hand? So if you have a 2-card hand, you have 52 cards, and you're choosing 2 of them. So that's 52, choose 2. And if you use your calculator, you're going to have to find this on your calculator. If you're using a TI-84 or TI-83, you need to go under the math button. So look for the button called math, which is really weird because what else was the rest of that stuff on your calculator for? Anyways, hit the math button, scroll over to the probability section. So go right until you get to probability, and you'll see under there's an NCR. If you're using another calculator, you got to look for a symbol that often looks like NCR. It's something like this, okay? And you'll get your number there. And just to test if you're getting the right number, the number is 1,326 ways of receiving those cards, which reminds you of why it is so interesting playing with 52 cards. There are so many unique 2-card hands, or if you have a 3-card hand, you can imagine the number of possibilities here. So we have 52, and we're choosing 3 of them, and suddenly you have 22,100 different hands you could receive. And many of our games that we play involve a 5-card hand. And so if you're dealing with a 5-card hand, you have a whopping 2,598,960 ways. So that's 52, choose 5, 2,598,960 ways of doing this. Whew. All right. What about if you have 10 people available? How many committees of 3 are there? Again, you would have 10 people. You're choosing 3. It would be 10, choose 3. And I imagine you can use your calculator by now to figure this out. 10 people. How many president, vice presidents, and secretaries are there? Well, I threw a little trick question in here to see if you're going to remember the past. So now, suddenly you have a president, a vice president, and a secretary. This is not a committee with 3 equal people. These are 3 very unequal people. So order matters here. So it's 10P3. And let's look at the difference between 10 choose 3 and 10P3. So if you have 10 choosing 3, you have 120 options, which we saw in the pizza question. But if you have 10P3, you suddenly have 720 different ways. All right, last little thing here. I want you to calculate the following. So type this into your calculator, and then so pause the video. To compare our answers. I want to look at 2 in specific here. So if you have C and then 2 numbers, this is our N and this is our R here, just like this is an N and that's an R. So this simply means 11. 11, choose 11, which is 1. Or here we have 5, choose 0, which is 1. If you have 5 people and you're trying to choose none of them, how many ways are there to do that? Well, simply don't choose them. That's one way. Okay, if you look at the rest of the answers, I want you to just look at all these 10 answers. The 10 choose 0, 10 choose 1, and then we move up to 10 choose 10. And this one I just put in here for fun. If you have 10 choose 11, if you have 10 people and you have 11 positions to fill, how many ways can you do that? Well, you just can't do it. That's when teacher's asking for volunteers and no one raises their hand, you have no volunteers. This is not possible. So this is when you need to be voluntold. All right, with the 10 choose zeros and 10 choose 1, let's take a look at them. You notice you got a 1, you got a 10, you got 45, you got 120. And at 10 choose 7, you got 120. And 10 choose 8, you got 45. And 10 choose 9, you got 10. And 10 choose 10, you got 1. Do you notice a symmetry in here? You got 1, 10, 45, 120. Afterwards, we go back down from 120, 45, 10, and 1. And did you happen to notice a symmetry as well when we were looking at this question here? Started at 5, and then it went to 10, 10, 5, 1. Do you notice where that might come from? Well, that's Pascal's triangle, isn't it? So if you look at Pascal's triangle, you will see that, I'll put it down here, this note, the n choose r, this is my row number in Pascal's triangle, and this is my position number. And this is really unique. Pascal's triangle gives us all of these answers. But of course, we have other ways to solve this as well, using our calculators or using the formula of n factorial over n minus r factorial, r factorial. I also want to note that, hey, why would it be that 10 choose 1 is equal to 10 choose 9? Well, you can think of it this way. If you are choosing one person out of 10, or if you're choosing 9 people out of 10, they're really the same thing, because if you're choosing 1, well, you're choosing one person. But if you're choosing 9, essentially you can look at the last person, you're leaving one person out. So it's like you're choosing to not include one person. In the same way, if you choose 2, that's no different than choosing 8, because choosing 2 is the same as not choosing 2 when given 8 people that you're choosing. You're choosing not to include 2. So there's nice symmetry about these combinations.